I do think it's important to talk about triglycerides because you're all going to, as you get older, you'll go, who gets their, like, physical? Do you guys get physicals every year? And there's, like, blood work with that, and then you get your triglycerides is one of the numbers that you probably don't have to look at yet because you guys are all in your early 20s. But eventually, when you get to my age and older, that's something that is an important number in your blood work, and it's important to understand how the food you eat connects to a triglyceride, what they are, etc. So this is them right here, a triglyceride. It's also known as triacylglycerol, or you'll see them abbreviated as TAG for triacylglycerol. A triglyceride is sort of the polymeric form of a fatty acid. So up until this point, all the biomolecules that we've seen have been ones in which the polymer can repeat itself ad infinitum, right? So you can have, there's not really a limit to how many nucleotides you can stick in a chain or how many carbohydrates in a polysaccharide or how many amino acids in a protein. However, there is this sort of limit on how many fatty acids can link up to one another. And it's the triglyceride. So the basic structure of this has 3 fatty acids and 1 molecule of glycerol. So we've seen a molecule very similar to glycerol already, haven't we? We've seen the molecule glyceraldehyde. You guys remember glyceraldehyde? It was the most simple of the sugars I showed you. It was a 3-carbon sugar, and it had 2 hydroxyl groups like you see here, but the first of those hydroxyl groups actually wasn't a hydroxyl, it was an aldehyde. So it was a double bond to the O, and that between the O and the carbon, the oxygen and the carbon in the first carbon, and then a chain of hydroxyls. That was glyceraldehyde. This is glycerol. Glycerol is a more reduced form, a less oxidized form of glyceraldehyde. And this glycerol molecule is going to react with the 3 fatty acids. Those fatty acids can be anything. They can be any fatty acid. It doesn't matter. I'm showing these 3 here. Those chain lengths, they're all saturated 12-carbon fatty acids. I guess that's, what is that, stearic acid? I think that might be stearic acid. But it can be any of them. It doesn't have to be that. So the reaction that joins the acid, the carboxylic acid of the fatty acid, and the alcohol group of the glycerol is called esterification. When we're making an ester, so like polyester is a molecule that has, where the units have a carboxylic acid and an alcohol on either end, and there's this ester formation that creates the chain. So esterification is what happens here to form the triglyceride, and if we look at it, esterification is a dehydration reaction or a condensation reaction, in that and we've seen those already, in that it basically takes water away from the 2 molecules and then links them up to form the C double bond O bond O to another carbon. So there's this oxygen that looks like an ether bridge, COC, but then there's a double bond O, and we call this group here an ester. Esters are interesting interesting functional groups. They often feature prominently in molecules that have different odors and flavors to us. We'll see that. Hopefully I'll get a chance to look at that when we talk about the Maillard reaction and some other reactions in cooking. But yeah, that's what a triglyceride is. So as I had said, the fatty acids that are all connected to one another don't have to be the same, and often they can be they're different. So they can have any degree of saturation or unsaturation, and different chain lengths, et cetera, et cetera. So here's a triglyceride with 3 totally different fatty acids on it. And because of this now, you can begin to appreciate that when you look at a number in your, for example, your blood profile, where it just is giving you a bulk triglyceride number, that number itself is not telling you a whole lot, because the triglycerides you have, they could be loaded with really beneficial polyunsaturated fatty acids, or they could be loaded with saturated fatty acids, right? That the character of the triglyceride matters. All right, so we can put fatty acids together and to make triglycerides, but we can go in the reverse direction and take triglycerides apart to form the free fatty acids, actually the sodium salts of them in this case, and recover the glycerol. So this process can either be base catalyzed or alkaline catalyzed, or acid catalyzed. And when it is done by a base, oh, my nose, I'm going to sneeze. We call it, pardon me, thank you. We call it saponification. So this is the process of taking a triglyceride and exposing it to aqueous, a strong base in the form of aqueous sodium hydroxide. So that's basically Drano. And if you treat triglyceride with Drano, aqueous sodium hydroxide, you get the sodium salt. So it's going to be an acid-base reaction here, a cleavage of the ester, an acid-base reaction, where the outcome are these ionized fats with sodium as the counter anion. So these molecules, these sodium salts of the fatty acids, these are what make soap. So this is what makes soap a soap. And the essential idea behind this is, maybe I'll use the board once. Ooh. I agree. Yes, that sucks. You have this fatty acid. It's useless. You have you can have these fatty acids line up with one another such that the charged head groups are all going to be in a row, and the greasy legs are all lined up as well, like you have seen in the diagram I showed you of a membrane of a cell, but they're smaller. They're not making the leaves they make end up being bubbles, soap bubbles, right? And so if you have dirt, a greasy bit of dirt, the greasy tails of these sodium salts of the fatty acids can arrange themselves around that piece of dirt, that greasy bit of whatever, and that is not going into solution very well just in water. And then the charged head groups point outwards and towards the water, and it solubilizes that greasy thing, that greasy molecule, the dirt, whatever it happens to be. That's how salt works, or soap works. So a common fatty acid that's used for this is palmitic acid, which can be derived from palm oil. And if you treat that with a strong base, you get sodium palmitate, which many of you, if you ever read the ingredients on the back of a bottle of shampoo, you'll see that as a very common ingredient in soap. The different properties of various soaps, like how well they deal with one type of dirt or another, one type of oil or another, how aggressive they are, the type of lather that they form, which is the bubbles that they form. The specifics of all of that is directly related to the chain length and whatever degree of saturation you have when you're making soap. So I know this isn't food, but it is pretty interesting how soap is made. Have you guys seen the movie Fight Club? Yeah, I mean, probably. Obviously, in that movie, this is all that they were doing. They were just taking fat and triglycerides and treating it with strong base. Making soap itself is actually quite an easy process in general, which is why it's such a common home industry. You can buy a lot of homemade soaps here in Maine that are made often from. Do you buy homemade soap? I leave buying soap to my wife, and she does sometimes buy homemade soap.
There is a special difference between homemade and factory soap.
One, supporting local economy. I tend to like soap that doesn't have a lot of fragrance in it. I don't really like fragrance. Nope. Okay. So the same thing can happen by acid, however. And if you use acid hydrolysis to break the triglyceride down, which is what happens in the body, it's usually acid catalyzed, the way your body is going to be utilizing those fatty acids. That's how you recover the original free fatty acid, is using an acid hydrolysis method. So your body's not producing soap inside of it. It's recovering the fatty acids, hydrolyzes the ester. All right. So I'm going to give just a little bit of an overview of how we utilize fats. We're all sort of, I'm going to head in that general direction. I'm going to stop prior to going down the deep well of the lipoproteins that I used to talk about last year. But so it begins. We have breakfast, and maybe I didn't, because I don't actually like fats for breakfast, but maybe you did have some eggs and bacon or something like that, and I have a little droplet of fat in my stomach. And because of the fact that the fats, these fatty acids, are hydrophobic, right? They're fats. It's going to form this droplet where the enzymes, specifically it's called a lipase, the enzyme that can break these fats down to use for whatever purpose the body's going to need them for, can't get to them because those proteins are water soluble, right? They're in solution in the water, in the aqueous environment of the stomach. So we're going to have to somehow break up this droplet of fat that we got, and which is the process of emulsification. That's what an emulsifier is. So emulsifiers are in a lot of foods, and it gives foods the unique textures that they have purely by the way in which they get fats to interact with hydrophilic environments, right? That's what a fat or an emulsion is. So the way the body does it, however, is to use what's called a bile salt. So bile is this is this molecule. There's several of them, but it's this category of molecules that are made in the liver, and we'll see what they look like in just a little bit. But these bile salts are also amphipathic molecules. So what does the word amphipathic mean?
Amphipathic.
Amanda knows. I don't know. You were like, you at least recognized the word. You've heard the word before. You looked off in the middle distance. Yeah, okay. Amphi, what is amph? I've gone through this root word. No.
Change.
AMPHI. What word am I trying to? Yeah, amphibian. And what is an amphibian? Right. What are those two things?
It breathes and it lives in water.
Yeah, it's out in the air and it's in the water, right? So an amphipathic molecule is one that likes both hydrophilic and hydrophobic environments, right? So I use that word on the first slide of this FAT sequence here to say that fatty acids are amphipathic, meaning there's the polar head group and there's the and the nonpolar tail. So bile salts are also amphipathic molecules that are going to help solubilize these big drops of triglycerol. Because you'll notice here, one of the things about a triglycerol, if we look back at that structure, you see that acid, the real polar end of the molecule that can, when you have a free fatty acid right here, this molecule can ionize. That hydrogen, that acidic proton can come off of there and does readily in aqueous environments, right? So this is a pretty polar molecule and more likely to form micelles and interact positively with an aqueous environment. However, when that acid group has been tied up in an ester and there's no longer the opportunity for that fatty acid to be charged, as in having ionized itself, it gets tied up in this. This triglyceride is way, way, way more hydrophobic as an entire molecule and not as amphipathic as one of these or the three of these free fatty acids, right? So by being in a triglyceride, we've packed them in there. It's a good way of having a high density of fatty acids in a single chain, but it's very hydrophobic. And so we need to break that up and resolubilize it, and we do that with bile salts. It's going to break up these fat droplets into much, much smaller clusters of fats so that the enzymes that are in your stomach, in the digestive tract, I should actually say in the duodenum and in the small intestine, the enzymes that specifically cause that cleavage of the triglyceride, which are called lipases, they can access the triglycerides and begin to liberate the free fatty acids and the monoglycerides. So a monoglyceride is simply the same molecule as a triglyceride, except there's only one ester formed, and the other two terminals on the glycerol molecule are just hydroxyl groups, free hydroxyls. You guys with all that? So a monoglyceride has one fatty acid attached to glycerol. Diglyceride has two, and a triglyceride is three, of course. So the what are called enterocytes. The prefix entero just means referring to the enteric system, your GI tract, your digestive tract. The cells of the digestive tract, the enterocytes, cannot absorb triglycerides, but they can absorb free fatty acids and monoglycerides. So once the GI tract has gotten them to that point, the cells of the GI tract are able to absorb them. All right, so we're gonna look at this process in a little bit more molecular detail, not again excruciating, but just a bit. So the process of emulsifying these triglycerides falls to the bile salts, and as I had just said, and bile salts are made of cholesterol. So, in the 80s and 90s, there was this big move towards eliminating cholesterol from your diet. And while there is some merit to that, the truth of the matter is that your body typically, you don't typically get enough cholesterol in your diet. Like most people, you really have to go out of your way to eat more cholesterol than your body needs, because cholesterol tends to run with fat, and so it's hard, and you need cholesterol to be able to absorb the fat. You understand? So the way to, if you were truly eating more cholesterol than you needed, you would have to engineer a diet, which would be difficult, where you're eating a lot of cholesterol but very little fat, which is difficult to do. So when they talk about eliminating cholesterol from the diet, that doesn't actually make much sense. If you have a problem with your cholesterol, there's a number of things that you need to do, but primarily they can all be summed up as managing the fats you consume rather than the cholesterol that is getting consumed in the food that you eat. So when they put cholesterol on nutrition labels, and that's fine, but that number is not actually especially useful, is what I'm trying to tell you. The thing that is useful is knowing what fats you're consuming, how much, and what, even more important, what type of fats. Like, for example, I don't know, hopefully I have a healthy heart, I don't know, but I could drop dead tomorrow. I have a fairly high-fat diet, but I try to choose the types of fats that I'm consuming, right? And we'll get to how that plays out nutritionally in a little bit here. Anyways, bile salts are made from cholesterol. And then there are these molecules called glycerophospholipids that I'm going to show you what that means in a little bit. And an important one is called lecithin. Lecithin, I don't know, is anybody here like a habitual label reader on the food that they eat? We had a couple of you did a podcast about ice cream. Lecithin is definitely an ingredient in a lot of types of ice cream, particularly like the cheaper ones. So we'll talk about what that molecule is and what it's actually doing in a bit. But all of it is the bile salts and lecithin are ways of emulsifying fats, breaking up big fat globs into like very small bits of fat that can be suspended in an aqueous environment. That's basically what an emulsion is. It's a suspension of fats in a liquid aqueous environment. Or it can be the other way. If there's a lot of fat, an emulsification can be suspension of aqueous components in a much more predominantly lipid environment as well. So, for example, an example of that would be: has anyone made oleo before? The kind of Italian origin of mayonnaise, where you're taking olive oil and egg yolk, and you're whipping it super fast with a little bit of lemon juice, adding lemon juice to it, and it like turns into that, oleo, which is sort of like mayonnaise. Has anyone had that stuff before? It's really good. Should try making it. Maybe we should make it in class. That would be a fun lab sometime. Okay, so Once you get them into, once all these fats are emulsified, then we have lipase, and we'll see what that means and what that looks like in a bit. So let's start with cholesterol. Cholesterol is it's a type of lipid. It is a type of fat that is in a category called the sterols, and it's made by every animal cell out there. All animal cells make cholesterol, specifically out of a molecule called acetyl-CoA. So acetyl-CoA, this molecule on the left over here, is, I didn't start with this. I started with fatty acids, but acetyl-CoA is really the building block of fats. It's the metabolic intermediate that not just is the building block of fats, but it also connects fats to carbohydrates. It's a 2-carbon molecule that you see there, an acetyl group that is connected to this coenzyme, basically a vitamin that it acts as a carrier for the 2-carbon acetyl group. Those 2 carbons that you see there, methyl group and an aldehyde group, though that's the fundamental building block that gets used to make lipids. Can also, it feeds into central metabolism. Carbohydrates can get broken down into acetyl-CoA as well. Anyways, there's a multi-step process, like a long, to what would all of you seem an incredibly painful biosynthetic pathway that your body goes through to get from acetyl-CoA up to cholesterol. So in an animal, all of the carbons in a cholesterol molecule originally started as carbons 1 and carbons 2 in acetyl-CoA, which is kind of interesting when you think about the isotope discussions we were having earlier in the semester about corn C3 versus C4 plants and the origin of the carbon. So all of the carbon that's in cholesterol, it shuttles through acetyl-CoA. And because of that, dietary sources of nutrition that lead to acetyl-CoA can be picked up in the fats in your body as well as via the carbohydrates you're consuming. All right. Looking at the sterols in general, there's this core that you see here. These 3 hexagonal rings, and I'm showing these as planar, but they're not. They're in that zigzag up and down chair form that that you guys saw in carbohydrates, right? But there's no hydroxyl groups. Just the core is these 3 fused hexagonal rings, cyclohexane rings, and then there's a cyclopentane ring, a 5-membered ring. So that forms the core of all of the steroid hormones. That core can get made into cholesterol by just sort of decorating it a little bit. You decorate it with this long chain of 8 carbons there, plus a couple other methyl groups. The one thing you'll notice here is on this end of the molecule, you've got a hydroxyl group, a free hydroxyl group, and this is going to be hydrophilic. All of this over here in cholesterol, all of the rest of this is hydrophobic. So cholesterol itself is also amphipathic. All right, it's also an amphipathic molecule. Because of that, cholesterol can insert itself into membranes in your body, and with the little hydroxyl group sticking up. So that hydroxyl group helps to orient the cholesterol, kind of like a float almost, that keeps it bobbing up towards the surface of the lipid membrane. And this crazy structure, I mean, look at the structure of cholesterol. It's a pretty wild structure. that structure does a lot to disrupt the order in the lipid membrane. I told you, we talked last time about solid fats versus liquid oils. And what was the structural thing that led to that difference between a fat and an oil? I know, it was a long weekend. Yeah. That's right. That's right. So unsaturated fats that have these double bonds in them that are all kinked up, they don't pack together very well. They have reduced amounts of, reduced density of hydrophobic interaction, and so they're more fluid, right? Likewise, cholesterol does not pack well. It doesn't pack well. It's a bony, pokey molecule that's got all these things sticking out of it in these ring forms. Ring forms are not super flexible, right? It's got a lot of sharp corners on it, much like these unsaturated fats. Because of that, cholesterol actually brings more sort of fluidity into the surface of cells, like in your body, in animal cells. The cholesterol keeps that the cells at a lower melting point. Right? So when you think about, for example, how does a wolf or something like that, how is it like a timber wolf able to walk on the snow and ice all year round without having shoes on? How do they do that? Because if you were to do that, your feet would freeze. The fat in your feet would turn solid and your feet would begin to freeze, right? So it's a function of the lipid profile in certain parts of that animal's body that enable that and change the melting point of those lipids. Anyways, once you have cholesterol, you can take cholesterol and make a whole bunch of other steroids out of it. So down on the left-hand corner is testosterone, and right adjacent to it is estradiol, related to estrogen. That's the mother of all the estrogenic compounds. They're really not that different than one another, are they? The difference between estrogen and testosterone is quite small, frankly. And then estradiol, progesterone, another important hormone in regulating the female body. Then there's other categories that are not androgenic. So there's aldosterone. Aldosterone functions in the kidney and helps with water balance and diuresis, like the elimination of water in the body. Cortisol, the stress hormone, the hormone that goes up and brings, all bad things that happen to you happen when cortisol is on the scene. Yeah, because sometimes there are times in your life when evolutionarily there was some sort of threat, some sort of stress, and you needed a chemical signal to the body that it was under stress and to cause changes in the metabolism and the basic fundamental activity of the cells in your body so that they were better able to deal with stress on the short term, right? So cortisol is meant to be to help you with the short-term response to stress. It is a benefit, right? So it makes you use energy more efficiently. It spikes your blood sugar, which maybe you need spiked blood sugar if you're running away from a saber-toothed tiger or something like that. I don't know, or whatever. When you're in the fight or flight response, sometimes you need a little bit of that. The problem becomes that system, the cortisol system, did not evolve in the modern sense, when people are just constantly stressing themselves on a day-to-day basis, it becomes pathologic in the long term, right? So it's just like, you have a fire alarm. Fire alarm is super obnoxious in the downtown dorm. You try to fry something, a piece of fish or whatever. You want to get that skin crispy on the bottom, and it's like you're setting off the alarm to where you're having a migraine for the rest of the day, the rest of the evening. Should we abolish fire alarms? No, of course not. They're there for a purpose, right? They're there for a purpose. So, anyways, cholesterol. So I guess I've already covered this concept here, but it's a structural component of all cell membranes. It helps give the structural integrity and fluidity. That little circle that you see on the top of it, that's that hydroxyl group that acts as the float, kind of keeping it up towards the top of the membrane. So cholesterol can be found in a wide range of foods that are all of animal origin. Since every animal cell out there is going to make cholesterol, any food that has animal in it is going to have some amount of cholesterol. This ranges from the yolk of an egg. So the egg yolk has a huge amount of cholesterol in it, in cheese and dairy, but everything from burgers, and that's a chunk of liver there. Liver is got quite a bit. Ice cream, cookies, all of it, cholesterol. So cholesterol can be used to make these bile salts. And so the way a bile salt works, it's broken up into three structural regions there, and there's a number of different ones. I'm just showing you glycolic acid here. So we have cholic acid that gets conjugated to glycine, which is one of the amino acids. There's some other amino acids, such as taurine, that can be used to make a bile salt, such as this taurochenodeoxycholic acid. Whew, it's a mouthful. Say that one fast 3 times. Anyways, when you look at these molecules, if you look at this structural motif up on the top, I'm not going to ask you to draw this and reproduce it for me or something. But what I do want you to notice is that in the original cholesterol, there was only this one hydroxyl group on the left that was hydrophilic, right? But we change it by adding all of these other hydrophilic groups on them. And remembering again that those rings that you see are not flat. They're this chair form. They're that like zigzag up and down chair form. Those hydroxyl groups and all those other hydrophilic groups are all on one side of this long sort of flat molecule. It's a large, flat, sort of a platform of a molecule. One side of that molecule is entirely hydrophobic. The other side is very hydrophilic. And so what it's able to do is get into a fat globule, which is super nonpolar, right? This food that's in our stomach that has a big fat globule. It can get broken up into very small ones as these molecules of bile salts pack themselves on the surface and create much, much smaller little droplets of fat with the triglycerides and the other lipids on the inside. All right, we're running out of time, but I want to get to glycerophospholipid. And what? Glycerophospholipid? It's a long word, yeah. Phospho. So a glycerophospholipid is made up of a diglyceride, so 2 fatty acids attached to the glycerol molecule, and then where the third fatty acid would be in a typical triglyceride, you have it attached to this other polar molecule, this by this phosphate bridge. All right, so we have two fatty acids, the glycerol, a phosphate, and then there's going to be this other much more polar molecule on the other end of it. So these glycerophospholipids are also really important in helping to bridge the gaps in these fat droplets. And they're extremely important in helping to emulsify the fat. Lecithin, that glycerophospholipid that I showed you a moment ago, that one is commonly extracted from, I think they get it from seaweed is a common source of lecithin. But they use it to give the consistency to like ice cream or really fatty foods that also have an aqueous component to them, right? It gives ice cream like a very smooth, stable consistency. All right, that's as far as I got on fats.